Okay, this is our chair. Here I will have hydrogen up, R down. This will be the ethyl in front, the hydroxy in front of the ester. I will have these two chair-like transition states. And then we need to check which is the most stable. If we remember the first example of the boron, when we have this R1 in the equatorial position, will be more stable. Isn't it? That means that all leads that this will be more stable. What happens here? That if we draw this, what is happening is that this R1 is crashing with the oxygen. Okay, maybe in this drawing it's not very clear that it's crashing, but if you build the molecular models, you will see that this R group is crashing with the oxygen. And this destabilizes this transition state. That means that now the right transition state is this, because here the R1 and the oxygen are far away, there are no interaction. This will be the good one. Okay? If you don't see it, that is difficult, you have to trust me. Here we have to avoid the interaction between this oxygen and this R1. Okay, that makes that this will be the good transition state. And now what we need to analyze is the reaction. And there are a big difference between now and the examples before. In the examples before, our carbonyl was the electrophile. That means the nucleophile attacks following a Burgin-Dunitz reaction, Burgin-Dunitz trajectory. Okay? But now this is the nucleophile. And remember that we have the pz orbitals with the electron here. Okay? That means that this pz orbital is the one that will do the nucleophilic attack. I will move the oxygen a little bit more to the right. I am not doing anything. I am only moving this a little bit more. Okay. That means that the attack will be up in this direction or down in this direction. And we are reacting this enolate with alkyl halide. Whatever it is, allyl halide. If we do an attack of an enolate to an alkyl halide, from the point of the alkyl halide, the reaction will go through SN2. That means we have here the leaving group, and we will have here the free substituents of the alkyl halide. Okay? And up will be the same. Because the SN2 always is attack from behind, okay, with inversion of configuration. And now if we saw this approach and this approach, clearly when the approach is from here, from down, these free substituents are crashing with R1 of the chair-like transition state. While the approach blue, the blue approach, is quite empty. That means it's not crashing with anyone. This is why the blue approach will be favored, will be the less energetic approach. If we do this, what we get is basically this will have the R2, that will be this altogether. I say that is R2. Then we will have here here we will have R1 and the high value. Right? This will be when this position attacks this position. If we draw it in the right drawing, that means in a normal projection, we will have R2, sorry, R1, this R1, the wedge inside, like at the beginning, this is never changing, and when we arrive here, what we have is that the R2 is coming to us, and here we have the S2. Okay, that means that we will have the anti-combo. Okay? These are the 3 examples that we shown today. Okay? Each one has his approximation, and you have to understand why we are choosing the most stable conformation or most stable transition state in each step. Here we form the 6-member ring with the lithium, and then we analyze which is the most stable 6-member ring, taking into account that when we have the R1 very close to this oxygen, this destabilizes. I mean that we have to get the R1 and this oxygen in different sites, okay? And then we have to analyze the trajectory of the nucleophile, taking into account that it's not anymore a Burgin-Dunitz trajectory, okay? It's an enolate, that means that it's 90 degrees up or 90 degrees down. And then we have to analyze that this is a SN2, and obviously the different substituents of the alkyl halide will interact with here almost nothing, and here will interact with R1. That means that will disfavor the red approach and will favor the blue approach. And then the only that we need is to draw the final product. Okay? Thank you very much for your attention, and see you in the next lecture.